When we perform calculations with a pen and paper, we often need to save intermediate results. And we may do this with, say, scrap paper. And in this case, the paper is acting as a form of external memory. And memory, no matter the form, takes up physical space. Computers contain memory. We can think of it as the scrap paper for the computer. And say when you construct an array to store values in your program, you require memory. And at the lowest level, computers read and store all instructions as a string of numbers. But how do you store numbers in a machine? This was a very difficult problem originally, especially when you need computers to hold their memory after the access to power is lost. This is known as non-volatile memory. The easiest difference for a machine to detect is simply a presence versus an absence of something. And this is how old punch cards would work. Along the top, we have some data, and the vertical columns contain a series of punched holes which represent each character. So computers really have two fingers, base 2, same as a light switch being on for 1 and off for 0. This is the smallest amount of information, a single difference, which we call a bit. But bits are powerful for storage because the amount of unique states grows exponentially as we add bits together. Remember, one light switch is 1 bit and it can store 2 states. But 2 light switches can store 4 unique states. And 8 light switches, or 8 bits, can store 256 unique states. And space is measured in bits. But the physical size of a bit depends on your method of storage. So how do computers store zeros and ones internally?
Modern data processing systems like these use thousands of magnetic cores. What are magnetic cores? They are tiny rings of nickel alloy or other magnetic materials. They have replaced vacuum tubes for many important functions in data processing systems.
And it allowed computers to store bits as clockwise versus counterclockwise magnetization direction, because each core could be magnetized in 2 different ways, depending which direction the current was applied.
Because a bit can be represented by any bistable device, and a magnetic core is a bistable device.
Later on, this was done using thin film magnetic disk, where we can think of as each bit as a tiny magnetic cell, which can be charged to store either a 1 or a 0. So long story short, the size of a bit has been rapidly shrinking since the days of punch cards. A hard drive in a modern computer can be thought of as billions of tiny magnetic cells. Now you may wonder, well, how small can these little magnetic cells be? And current research at IBM is pushing this to the atomic level, where they have shown 12 iron atoms can work together as a stable magnetic unit, where they're able to store a 1 or a 0 depending on how they're oriented. And this is approaching the theoretical limit where we would hold a single bit on a single atom. And interestingly, IBM estimates that we could put around 1 quadrillion bits of information in a handheld device the size of an iPod with atomic storage. And let's call this a super drive. It doesn't even exist yet as a hypothetical example. A small handheld super drive using atomic storage would hold 1,000 terabits, which is 1,000 trillion switches, or more commonly known as 125 terabytes in the palm of your hand. Or to use an example everyone can understand, 125 terabytes is the same as having a 1,250 kilometer long bookshelf in the palm of your hand. And this is what the future of memory looks like. Will we ever be able to store a bit on something smaller than an atom?